Okay, let's start with 13.1, another chapter. But before we start, I've uploaded several optional things, helps for you. So here's your class. You should be seeing your class here. So what I did is we're going to be doing, you do in certain things, you do the same things over and over and over again. You'll certainly be doing some of the things we're doing now over again when you take intermediate algebra. So these are videos: optional review, optional review, optional review. So factorization by special products. That's not, I'll put them in order. Factorization of trinomials. Table method for computing the LCD and the GCF. We'll be doing that a little bit today. Factorization of trinomials, we'll be doing that in the next lecture. And factorization by special products, that we actually do in this chapter. And here is an optional file on how to do or make the LCD and the GCF table. It's a nice little reference. It's got two examples, and you should look at both of those examples. The third example you won't have to deal with. That'll be something that you'll use when you take intermediate algebra. These two videos aren't my blue screen with yellow writing videos. That was right when I was experimenting and I was using something similar to the doc cam. At any rate, all of these are optional just in case you need them. So let's go and bring up. So we want to find the greatest common factor, and I'm going to teach you a way to do it, and it's really easy. This is one concept students usually get without me even explaining it. So for your case, we're just going to talk about the greatest common factor of two integers. So we're not talking about fractions. And we'll call those integers a and b, is denoted by the GCF of a comma b. Now, if you read in my other thing, just like the least common denominator, some call it the least common factor. The greatest common factor is sometimes called the greatest common divisor, the GCD. Well, the greatest common factor of integers, a and b, is denoted by GCF of AB. You can just read that as greatest common factor of A and B, and is another number, integer in your case, k, such that a divided by k leaves no remainder. Another way of saying this is k evenly divides a, and b divided by k also leaves no remainder. So those are the two. That's the first criteria. And then the second criteria is going to be the following. K is the largest, or I guess I should have used the term greatest, integer for which this is true. So let's just go to some examples, and I'll introduce some properties as we go on. So I'm showing you how to do this. A lot of you can do it in your head, and you're perfectly fine to do it in your head. So we want to find the greatest common factor. So this is 1a of 16 and 6. So we're going to use a table method. The reason we're going to use the table method is it's good to have down, because once you have the table method, you can find the LCD and the GCF really simply, and it's easy to extend this method to more difficult things like finding the greatest common factor or the LCD of polynomials. And you won't do that until the very end of intermediate algebra, but I will tell you right now that's very problematic for students. If they know the table method, they're okay. So the first thing we're going to do is we're going to do the factor tree for 6 and 16. So 6 is divided by 2 and 3, so that's it. These are primes. So 6 is equal to 2 times 3. And for 16, I'm going to divide it by 2. I get 8. I'm going to divide it by 2 and get 4. I'm going to divide it by 2 and get 2. So I've got 1, 2, 3. So 16 is equal to raised to the 4th power. So I take a look, and I make my table. My table is going to be it's going to be identical to the table that we make for finding the LCD. And in the columns, I'm going to have my 6 and my 16, it doesn't matter. And the prime factors, just the prime factors. So there's a 2, and there's a 2, and a 3. Now all I want to do is, just like we've done before, I want to take note, how many factors of 2 are in 6? There's just 1. How many factors of 3 are in 6? There's 1. How many factors of 2 are in 16? There's 4. How many factors of 3 are in 16? There's 0. So I've got my table filled in. Identical to how we did the LCD table. But now we're actually going to derive the GCF. So the GCF is equal to, take each one of my primes, 2 raised to some power, just like when we were doing the LCD, times 3 raised to some power. And how do I find the powers? Here is the difference. I look at, let me erase this. I look at the smallest number in each of the rows. When I was doing the LCD, I looked at the largest number. So the smallest number in the row of the 2's is a 1, and the smallest number in the rows of the 3 is a 0. So since 3 to the 0th power is 1, this is just equal to 2. So the greatest common factor of 16 and 6 is equal to 2. Okay, so let's do it again. Now I know a lot of you, especially when it comes to integers, it's going to be pretty easy, and you can do this in your head, but we're not going to do it in our head. We're going to do it by the table method in each case. And then once you know the table method, you can decide to use it if you want. So again, we're going to find the GCF of 18 and 24. And once you know the table method, you can actually shorten it. So 18, we're going to do the prime factorization of 18. 18 is divisible by 2. 18 divided by 2 is 9. 9 divided by 3 is 3. So 18 is equal to 2 times 3 squared. Now let's do the same thing for 24. 24 is divisible by 2. 24 divided by 2 is 12. 12 is also divisible by 2. And that becomes 4. Sorry, not 4. 6. 6 is divisible by 2, and I get 3. So here are all of my primes. So 24 is equal to how many factors of 2 do I have? I have 3. So let's make my table. So primes. And I have 2s and 3s. Just a 2 and a 3. And here I put 18. And here I put my other number, 24. Now I just take note of how many I have in each. So how many 2s are in 18? Just 1. How many 3s are in 18? 2. When I say how many 3s, I mean how many factors of 3. How many factors of 2 are in 24? I have 3. How many factors of 3 are in 24? I just have 1. So now I'm ready to compute the GCF. It's 2 raised to the smallest number in this row, which is 1. And it's 3 raised to the smallest number in that row. So 2 times 3 is equal to 6. So the GCF is equal to 6. Let's check our properties. Is 18 divisible by 6? Sure. It's divisible by 6 evenly. Is 24 divisible by 6? It sure is. 4. And that's the largest number that divides both of them evenly. So that's another way of thinking about the GCF, is the GCF of two numbers is the largest number that divides all of them evenly. That's exactly the same thing as the definition I gave you. No. There we go. So again, let's do 1C. We want to find the GCF of 15 and 21. And now we're going to actually, I'm going to show you a different way to do it. There's the table method always. But let's just look at the prime factorization. 15 is divisible by 5, clearly, times 3. So 15 is equal to 3 times 5. And 21 is equal to 3 times 7. So clearly my list of primes are going to be 3, 5, and 7. But if you think about it, 15 and 21, that 5 and 7 are not factors in both of them. So with 5, I'm going to get a 0, and with 7, I'm going to get a 0. And as soon as you have a 0 in a row, that means it's excluded. It turns into 1. And of course, they both have one factor of 3. So the greatest common factor, here are all of the factors, and they literally share only one factor, which is 3. So the greatest common factor is 3. Now we will do it with 3 numbers. 1D. We want to find the GCF of 12, 28, and 40. So 12, we just figured that out, but let's do it again. So 12 is equal to 2 squared times 3. 28 is divisible by 7. 7 times 4 is 28. Let's do it the easy way. Sorry. I mean, you're fine to do it this way, but I've been doing it in a way, we might as well keep it systematically. 28 is clearly divisible by 2. So 28 divided by 2 is 14. And 14 is clearly divisible by 2. And that gives me 7. So 28 is, well, I have two 2's. 2 factors of 2, so that's 2 squared times 7. And finally, down here we have 40. So 40 divisible is clearly divisible by 2, and 40 divided by 2 is 20. 20 is clearly divisible by 2, so that gives me 10. 10 is still divisible by 2, and that gives me 5. So 40 is equal to 2 cubed times 5. So if it's screaming out to you that the greatest common factor is equal to 4, then you're doing well. Let's go ahead and discover it by our table. Primes. And I have 12, 28, and 40. So I have a 2, and then I have a 3, I have a 7, and a 5, and it does not make any difference which order you write them in. None whatsoever. There's no reason they have to be from smaller to larger. Makes no difference. So let's do 12. How many 2's are in 12? 2. 2 are in 12. How many 3's are in 12? 1. How many 7's are in 12? 0. How many 5's are in 12 is 0. That already tells you that 7 and 5, as soon as the 0 appears, you know 7 and 5 are not going to be part of the factorization of the greatest common factor. Let's go to 28. How many 2's appear? 2, 0 3's, 1 7, 0 5's. I really don't even have to look at it now. I know right now that the only common factor is going to be some power of 2, because as soon as a 0 appears, then it's out as a factor. And 40 has 3, 0, 0, 0, 3, 0, 7s, and 1, 5. And the reason I went ahead and filled the whole thing in is because I'm going to show you something. The GCF is equal to, I didn't want to do that, I just want to make it a little bit smaller, 2 raised to the smallest power times 3 raised to the smallest number times 7 raised to the smallest number times 5 raised to the smallest number. Well, 2 squared is 4, 3 to the 0th, 7 to the 0th, 5 to the 0th is 1. Why did I bother to do that? Because I want to show you how nice it is. Once I have the table, I can also compute the LCD. For the LCD, I take the largest of the numbers. So that's the difference. The LCD is quite a bit larger than the GCF. The GCF is much easier to find, simply because as soon as you find that a factor of a number like 5 does not occur in all the others, you don't have to worry about it. So with the GCF, you can eliminate an awful lot of stuff. Literally, for the LCD, the table method is really the way to go. So let's go on. We figured out that. So here is how we're going to do the next. I'm going to give you a theorem. So we're going to be adding variable terms. So the GCD of x to the m and x to the n. So clearly n is a whole number. Let's make n a natural number. Let's not include 0 in the set. N is a natural number. N and M are natural numbers. Sorry. So we have that M and N are natural numbers. And this is a good time to review what a natural number is. They're numbers, they're counting numbers. It's at 1, 2, 3, and it goes on forever. Well, the GCD of x to the m and x to the n, so notice that the bases are the same, is x raised to the smallest of x, sorry, not x, of m or n. For example, x to the 7th and x to the 3rd. So the GCD of x to the 7th and x to the 3rd is equal to x to the 3rd. The GCD of m and m to the 3rd is equal to m, because m has an unwritten exponent of 1. The GCD of z to the 10th and z to the 7th is equal to z to the 7th. So now let's actually use some of these to put together how to find the GCD of variable terms. So we'll look at 2a. We want to find, did you hear me say the GCD? Just as a reminder, I said it earlier, the GCF and the GCD are the same. Greatest common factor, greatest common divisor. It's the same thing happens with the LCD and the LCF. And I have many times probably used GCD more than GCF, so I will probably slip and say GCD, but they're exactly the same, and I don't know why. But anyway, the GCF of 15m squared times 25m to the 5th. Well, it's equal to the GCD of 15 and 25 times the GCD of m squared and m to the 5th. So the GCD of m squared and m to the 5th is really easy. We choose the smallest exponent. And the GCD of 15 and 25th, well, 15 is equal to 3 times 5, and 25 is equal to 5 times 5. So 3 doesn't appear, and we choose the least number of times that 5 appears. So the GCD of 15 and 25 is 5. And 5 times m squared is 5m squared. So I'm not going to do the table method every time we look at the GCD of two numbers. I've kind of started you out, and you can use it at every time until you get good enough. I want to show you really fast. It's going to be coming soon, but I'm going to go ahead and slightly alter this problem because I just want to. Suppose I have the GCF of 15m squared and 25. Well, since there is no m term, you just ignore it. It just becomes the GCD of 15 and 25. Suppose I wanted to find the GCF of 15m squared z to the fifth and 25z to the fourth. Then you use again the GCF of 15 and 25, and each term does not have an m term, so you just skip the m term and you just do the GCD of z to the fifth and z to the fourth. So that's going to be easy. We found out the GCF of 15 and 25 is 5, and the GCD of these is the lowest power, so 5z to the fourth. So GCF, GCDs, I know I'm saying both of them. I hope it's not driving you crazy, but get used to it. It's pretty simple to compute. That's what makes it good. So let's do number 2b. So we want to find the GCF of 40x squared and 20x to the seventh. So again, that's equal to the GCF of 40 and 20 times the GCF of x squared and x to the seventh. And here is a special theorem. So let's go back over now. I gave you some theorems regarding the LCD. The GCF of A and B, it always exists, and it's always greater than equal to 1. So A and B are real are integers. But it's always less than or equal to the smallest of A or B. So the question is, when is it actually equal to the smallest of these two numbers? It's equal to the smallest whenever B is, which is the larger of the two, is evenly divisible by A. So I'm going to say assume, I don't have values here, assume A is the smaller. So why did I give you that? 20 evenly divides 40. So the GCF of 40 and 20 is 20. And the GCF of x squared and x to the 7 is x squared. So let's look at this again. The GCF of 3 and 21. Well, it can't be any greater than 3, but it can be equal to 3 if 3 divides 21, and it does. So that's equal to 3. The GCF of 7 and 35. Well, it's less than or equal to 7. It's equal to 7 if 7 evenly divides 35, and it does. The GCF of 2 and 16. Well, it can't be any greater than 2, but it has to be at least 1. It's actually equal to 2 if 2 evenly divides the larger of the two number, and it does. So we're going to be kind of using that to completely get around doing the table. So here we're going to do 2C. So I want to find the GCF of minus 28 x to the fourth and 56 x to the fifth. So when you have a negative, just ignore the negative. So let's look at 28. That's 2 times 14 times 2 times 7. So that's 2 squared times 7. 56 is equal to 7 times 8. Hence, 28 divides 56 because 8 is equal to 2 to the third. So 28 evenly divides 56. Either way it goes, the GCF, just ignore the negative of minus 28. You can put it in there in 56. But I said it's going to be greater than or equal to 1, so it's going to be positive times the GCF of x to the fourth and x to the fifth. So that's going to be 28. Take the positive value, and that's going to be x to the fourth. Sometimes you might want to factor out a minus 1 as well, but for right now, we're just going to take the positive value and not worry about it. Because it's much nicer to have this. The GCF of two numbers, two integers a and b, is always greater than or equal to 1, but less than or equal to the smallest of a or b. So, do another example. 2D. Let's find the GCF of 21 m squared n to the fifth 35 times m times n to the fourth. Well, this is going to be equal to the GCF of the integers 21 and 35. So that sometimes takes some calculation, but when we get to the variable terms, it's really easy. Since n appears in both terms, I have to deal with it. So that's n to the fifth, and it doesn't matter which order you do these in, times the GCF of m squared and m. So the GCF of 21, well, this is 3 times 7, and this is 7 times 5, so that's just going to be 7. And then we take the smallest power, n to the fourth, m, because I don't have a power there, but when it's not written, it's understood to be 1. So that's what the GCF is. Good. So now, what was all of this about? It's about factoring. We're getting ready to factor. The words sometimes just strike dread into so many algebra students. But if you're taught right, factoring is not only fun, it's easy. So here we are at 3a. So we're asked to factor out the GCF. So I'm just going to do a few examples. So basically, the process is we are changing a sum to a non-trivial product of a term times a sum. So here's an example. Remember distribution A times B plus C? That's equal by distribution A times B plus A times C. So basically, we're going to be given this, and we want to go over to here. So if you think about the GCF of these two terms, it's A. So once I factor out A, that's the non-trivial product of some term times a sum. When I say non-trivial, that means the factor that we pull out is not equal to 1. It could be equal to -1, but it's not equal to 1. So let's start here. So we have 5a plus 15. So I ask myself, what is the GCF of those two terms? 5a and 15. Well, since both terms don't have an a, that's the same as the GCF of 5 and 15. And since 15 is evenly divisible by 5, it's just equal to 5. So here's the process. I write down parentheses. Whatever my GCF is, I put it on the outside of my parentheses. And here we go. 5a divided by 5 is a. Plus 15 divided by 5 is 3. And I'm done. I factored out the GCF. Now let's just check to see that these two are correct. That this and this are the same. Well, by distribution, 5 times a is 5a, and 5 times plus 3 is 15. So these two are the same. Notice this is a sum. This is the product of some non-trivial number, meaning it's not 1, and a sum. And that's the whole process. It's a very, very powerful tool in mathematics, extremely powerful. So we're going to do, this is 3b. So we want to factor out the GCF of 56z plus 8. So since z does not occur in both terms, then all I have to do is find the GCF of 56 and 8. But again, since the smaller number, 8, evenly divides the larger number, 56, by the theorem, that's equal to 8. So here we start. Underneath, I write in parentheses, and I put my GCF on the outside. So 56z divided by 8. 56z divided by 8 is the same as 56 divided by 8 times z, which is 7z. So that becomes 7z. Sorry, I crossed my both z's and 7. And then 8 divided by 8 is 1. So that I just factored out of 8. So that's 8 times 7z plus 1. So not so bad, right? Now let's do 3c. We want to factor out the GCF of y cubed plus 2y. So that's going to be the GCF of 1 and 2, because remember, this does have a coefficient. It's unwritten, but it's 1, times the GCF of y cubed and y. Well, 1 evenly divides 2, so that's 1. And then I just take the smallest exponent of the factors. So the GCF is equal to 1 times y, which is y. So I write my parentheses underneath of it until you get good at this. I bring my GCF out first. So y cubed divided by y. Well, that's y squared. So I have 3 y's in top, 1 in the bottom. The 3 are going to win, but they have to give up one of them, and that's how I get the 2. Plus 2y divided by y is just a 2. So 2y divided by y, the y's cancel. So that's the factorization. Okay, so let's go to my next page. So we're going to do all of these. The more practice you get, everything about the GCF was just warm-ups to do the previous 3 problems I just did and the remaining 6. So I guess this is still 3D. So 3D, we have 5x cubed plus 10x to the 4th. So I want to find the GCF of 5 and 10, how easy it is using my theorem times the GCF of x cubed and x to the 4th. Well, since 5 evenly divides 10, that's going to be a 5. And then I take the smallest power. So it's 5x cubed. So I'll bring out my 5x cubed. So 5x cubed divided by 5x cubed is 1. And plus 10x to the 4th divided by 5x cubed. So if you need to do it on the side, that's equal to 10 divided by 5 times x to the 4th over x cubed. Well, 10 divided by 5 is 2, x to the 4th over x cubed. Well, the numerator has 1 factor more than the denominator, but it has to lose 3 of them, so it only retains 1. A lot of you can do this in your head, but that is what they're looking for, is right here. So now we have to find the GCF of 3 terms. 6z to the 5th, 8z to the 3rd minus 12z. So I have to find the GCF of 16, 8, and 12. You can just ignore the negative and multiply it times the GCF of z to the 5th, z to the 3rd, and z. And I hope a lot of you says, oh, I don't need to do this anymore. I've got this. You can just look at it and you're going to choose the smallest power of the variable. So 16 is equal to 2 to the 4th. So the greatest common factor is going to be 2. 8 is equal to 2/3, and 12 is equal to 2 squared times 3. So the common factors they have are 2's, and the largest, we take the smallest exponent, so it's 2 squared, or in other words, 4z. So 16z to the 5th plus 8z cubed minus 12z. So I'll put everything in parentheses underneath. I take my GCF and I put it out front. 16 divided by 4 is 4. Z to the 5th divided by z is z to the 4th. 8 divided by 4 is 2. Z cubed divided by z is z squared. Minus 12 divided by 4 is minus 3. Z divided by z is 1. So that's it. If you want, you can scoot in your parentheses a little bit closer. That's purely an aesthetic thing, but that is the factorization of E. Now finally we get something that is a little bit challenging. So F is x times y squared minus 2 plus 3 times y squared minus 2. So my factors are x, y squared minus 2. That's a factor because that whole sum, or actually difference, is being multiplied. And 3. Those are my factors. So let's do my table. My primes, here I'm going to put parentheses there, are x, 3, because x can't be factored, 3 can't be factored, it's prime, and the y squared minus 2. I can't pull out. It has no GCF. I cannot factor it. So I have x times y squared minus 2. That's one of my terms. And the other term is 3 times y squared minus 2. I hope you can see it. This has one factor of x, 0 factors of 3, 1 factor of x squared minus 2. This has 0 factors of x, 1 factor of 3, and 1 factor of y squared minus 2. So the GCF of those two terms is equal to y squared minus 2, and you want to keep it in parentheses. So here we go. I make my parentheses, and I put my GCF, y squared minus 2, out in front. And you want it in parentheses because this is a factor. This is taken together. So x times y squared minus 2 divided by y squared minus 2 just leaves an x. 3 times y squared minus 2 divided by y squared minus 2 just leaves a 3. So my factorization is y squared minus 2, I'm going to rewrite this, people, times x plus 3. So let's do that again, just right down here. X times y squared minus 2 divided by y squared minus 2. As in all cases, when I find a common factor, remember that's the reason we want to keep it in parentheses. Those are the exact same number. Hence, I can cancel them out. Good. And that's going to be the exact insight that we're going to need by this process called factor by grouping. There is the whole process of this is leading up on how to factor a trinomial. And one method of factoring a trinomial is to factor it by grouping. That's not going to be the method I'm going to show you. As a matter of fact, I'm going to show you a different method that is given to you in the book or what you normally find elsewhere. There's variations of the method, and the reason I have chosen this is it seems to be really easy, and students seem to remember it after the semester ends. So we want to factor this. The problem is the GCF of all four of these terms is 1. And that's my trivial factor. So if I want, I can just put them in, I can put these in parentheses and multiply it by 1, that gives me absolutely nothing. No information whatsoever there. So I'm going to erase it. Well, I don't, yeah, I'm going to erase it. So this is called factoring by grouping. So literally we have a sum of 4 terms, and we're going to reduce it into a product of 2 binomials. So what you do is I look at the first group of 2 and the second group of 2. And I want to find the GCF of the first group, 8y squared and 12y. And that's going to be 4y. Then you want to find the GCF of the second group of 10y and 15. And that's going to be 5. So what we do is we group these. Now I'm going to put a plus here right now, but it could turn out that we have to do something else later on. It's called factoring out a negative. So that could turn into a minus later on. So here's the GCF of my first group. So I'm going to put a 4y right there. So let's start. 8y squared divided by 4y. So 8 divided by 4 is 2. Y squared divided by y is y. Minus 12 divided by 4 is minus 3. And y divided by y is 1. GCF of my next group is 5. 10y divided by 5 is the same as 10 divided by 5, which is 2, and y divided by 1. Minus 15 divided by 5 is minus 3. Well, looky there. Now, as it turns out, I reduced a sum of 4 terms to a sum of 2 terms. So what is the GCF of these 2 terms? Well, the only thing that they share in common is this factor of 2y minus 3. So let's factor it. So my GCF is the factor of 2y minus 3, and it needs to be put in parentheses. So 4y times 2y minus 3 divided by 2y minus 3 leaves me a 4y. 5 times 2y minus 3 divided by 2y minus 3 leaves a 5. So look what I did. I turned a sum of 4 terms into the product of 2 binomials. So this is a binomial in the variable y, and this is a binomial in the variable y. Interesting. Not only interesting, but mathematically very useful. So now that you kind of see the drill, you might want to try the next one on your own. So again, we have, whenever you see a sum of four terms, think about factoring by grouping. And we're kind enough that we actually group them in such a way that it works out. You don't have to rearrange them. So again, the GCF of all of these, well, there's not an A term in all of them, so that's it. And this is 3 times 5, 2 times 5, but there is no factor of 5 and 6 done. So the GCF is 1. So I can't in any way simplify this the way it is. I cannot factor out anything in all 4 terms. But what about if I take them 2 terms at a time? what's the GCF of 15 a to the 6th and 25 a cubed? Well, it's going to be 5 a cubed. And what's the GCF of 6a cubed and 10? Well, that's going to be equal to 2. So now we're getting ready to factor it out. We take each term by itself. So I pull out the GCF, which is 5a cubed. So 15a to the 6th divided by 5a cubed. Well, 15 divided by 5 is 3. A to the 6th divided by a cubed is a to the 3rd. Minus 25 divided by 5 is minus 5. A cubed divided by a cubed is 1. So let's tighten these up. Doesn't really matter, but I'm sensitive about running out of space. So let's look at the next one. I'm going to pull out the 2. And that's a positive 2. So 6a cubed divided by 2. Minus 6a cubed divided by 2. So that's minus 6 divided by 2 is minus 3a cubed. And 10 divided by 2 is plus 5. But here's the problem. Three a cubed minus 5 and minus 3a cubed plus 5. Each term differs by the other by a sign. The 3a squared here and negative 3a squared here. Minus 5 here, plus 5 here. When that happens, what we do is we factor out a negative. So remember, if I have minus a plus b, I can factor out a negative by changing the sign of what's in parentheses. So I'm literally going to leave my first term as it is. I'm not going to factor out the negative there. I could, but it's nasty looking, I guess. I don't know. I don't like to say. But I'm going to factor a minus 1 out here. So a minus 1 is going to be multiplied by all of this. A minus 1. But 2 times a minus 1 is going to be a minus 2. And how do I factor it? I changed the signs of each of my terms. So minus 3a cubed becomes 3a cubed, and plus 5 becomes minus 5. Hey, great! Now I have two factors that are identical. So now I can go ahead and I can factor out the common factor, which is 3a cubed minus 5. And you always want to put that in parentheses because it's a factor. 3a cubed minus 5. And 5a cubed times 3a cubed minus 5 divided by 3a cubed minus 5 leaves a 5a cubed. Minus 2 times 3a cubed minus 5 divided by 3a cubed minus 5 leaves a minus 2. So I took a sum of 4 terms and turned it into the product of two binomials. Okay, so that's it for 13.1.